Participants have already joined, and they are joining. Many participants are joining soon. So I request you to kindly start the session. Thank you.
Yes. So welcome everybody. I hope you had a good lecture already this morning. So we will go on with our. Excuse me. So is there feedback from my? No, micro is off. Okay. So I will again share my screen. Just a second. Yesterday we were talking about introduction, some motivation, some simple examples. So this triangle, put it like this, just going up and down. And then we more or less, the last point of the lecture was a general one period model. Let me see. Where we had formalized the wrong one. We will formalize the financial market. And we have seen that we can reformulate it in terms of a kind of matrix where you have all the potential values in all your assets in 1 year time or one time period. Just a second. I have to restart the other computer because I thought it would. Sorry for this. And then we had the non-arbitrage condition. Okay, let me see up. No, too fast. Now we use the separating hyperplane theorem, and I want to show you the proper picture for this again. Oh, now I have to share. I did share. Sorry, I'm now sharing. Share. Okay. Yeah. Okay, so this was after the introduction, and where we have seen the binomial tree, which is a kind of the standard example of from a mathematical point of view, where the underlying asset is just moving like a random walk, going up and down in each step. Random walk, it's right and left. Here it's up and down because it's a kind of a geometric random walk. And we have seen on this tree, we can derive the replication portfolio in order to get the price of an option as an initial cost of a replicating portfolio. And this is a basic scheme in financial mathematics, how to price in the arbitrage. Basically, it's a non-arbitrage method, such that if value of a portfolio, or that we have two portfolios which as a future time have the same value, then by non-arbitrage we should have the same value any other time before the final time. And as typically in the derivative, you know the value as a function of the underlying asset as a final time at the execution time, and then you go back in the binomial tree in this example. And so at each node in the tree, in each branch of the tree, you can replicate. And so you do it recursively, and you finally come up times 0, where you have the price of the option as the price of the replicating portfolio. As I said, that's just one simple example. It's very important. But from a theoretical point of view, of course, your one-period model, even it might be more diverse. This means here we have formulated the one-dimensional model, which has n states, capital N states, capital N states. Capital N states, the number of states, number of assets, d plus 1, 0, usually it's a riskless asset. And then you can store somehow the information in a matrix, and everything which you, more or less a market is in the matrix consisting of future states of values of the portfolio, of the underlying strategy, and the initial value S0, this vector. And the portfolio is then just a vector of dimension d plus 1, telling you how much you invest in this one trading period into the assets. And then we had said, okay, non-arbitrage is meaning that if you invest nothing at the beginning, you won't get any gain in the sense. Gain means everything, there's no loss, and in one scenario you have a gain. So that's basically then non-arbitrage. This was the main theorem. So that you have this vector psi in Rn, and the number of states, so omega 1 to omega n, the different potential states. And this vector space, you have a positive, strictly positive vector such that this matrix S, where you have, that's of dimension, there's the n states, it's a matrix, and you have, for each state, you have the assets, you have the number of assets, d plus 1 assets. That's your matrix S. And you apply to this what's called the state vector later, and you get the initial vector. That's somewhere kind of a pushback. So that's going backward in one step, if this is possible. It's going from the future states, going back by psi to the current values. And as I said, that's like the martingale property later, as we will see, a expectation of S1 time 1 equals S0. And E expectation is also linear functional. So in finite spaces, it's all linear algebra. Okay. So I want to show you the picture which is used, namely the picture for the separating hyperplane theorem. So let me just look for a moment whether I find it also here. Should be this picture. I try to draw a picture for you. Okay, that's the situation. The gamma is a vector space in, that's Rn. Of course, as usual, you can only draw in R2. So imagine these are all Rn. These are the states. And sorry, I can't draw the problem is I can't draw here. Just a second. I will open another one. What's going on? Okay, that's the case of arbitrage freeness. Yeah, gamma. This is the first entry of gamma is always a subspace in Rn plus 1, a linear subspace of dimension. And here you have the reachable. Yeah? These are all claims you can reach. Yeah? So basically, no. Yeah? So we translate the property of absence of arbitrage into this one. Yeah? We are now drawing the picture. Yeah? Where gamma and k, yeah, k are all strictly positive vectors, yeah, with the property that they add up of 1. Yeah? That's where we finally want to find the psi. Yeah? And if this is empty, we are in this picture. Can't switch here. How do I get rid? Ah. How do I get to the other one? No. I don't like online teaching. Huh? How do I get back to my other? To this one. Yeah? So we have the situation that this is empty. Yeah? These are a set of positive vectors, which are also weights, k. And gamma is a set where you find the arbitrage. That's the image of all trading strategy. When the first entry you have the minus starting value, and the other one is a vector of all values in that's S minus S0 psi. And here you have the matrix, all values transposed. That's all what's called the reachable values you can get with your portfolio phi. And if this is empty, then you can find this lambda. Of course, in this simple picture, there's only 2 vectors which are rectangular which have which are orthogonal to this hyperplane, this one and mine. But you see all the angles between points in this K and this one are smaller than 90 degrees. Meaning the scalar product is positive. That's separating hyperplane. But we apply to this situation, this one's the gamma are the reachable claims, and there's no the portfolios, so the values of portfolios in the next time step, and this gives you the state vector finally, lambda, which we later call psi. So you can see if you have the situation where you don't have it, that's the situation where you have an arbitrage. This one is the value of the arbitrage. So this is the image. The gamma is also can you write as the image, let's say, of phi, of a trading strategy, but image in the sense it gives you the minus the starting value and plus and all the future values in all the n states. If you have an arbitrage, this one, this point, this red point here, this intersection is one. This one is one. It's an image, it's a value of the arbitrage strategy. But then you see all the angles here are larger than 90 degrees. Okay? So then you don't get a vector lambda with the two properties that it is orthogonal to the values, current value future minus current value future values, and it has an angle which is larger than 90%, smaller than 90%. So that's here you have an arbitrage, but if you don't have an arbitrage, you find, in this case, there's only one, you see that this orthogonal vector to this hyperplane has an angle smaller than 90%. Okay? Okay, this is a basic step. You construct the state vector, which we have done yesterday. And from the state vector, you get this lambda. And then you get this psi. And this is called state price vector or deflator because it gives values or weights on the n states. Each of the n future states get a weight psi I. And so if we rescale this, so we get a probability. So these are then what's later called the martingale probabilities. So you see reachable claims. There's kind of a duality between reachable claims, which are described by their orthogonal vector, and probabilities. Okay. This. Okay. Once you have constructed these probabilities, the last step is to say, okay, our first asset here, we use a property that this is a riskless asset. So the connection in the riskless asset between future times and current time, between t and 0, of course, that's somehow notation should be like this. Huh? This is 0 and this is t. Okay, yeah, this tells you this is a riskless asset. Yeah, if you take this asset with a number 0, this should be riskless. No? So if you rewrite all this, you see that under the new probability measure, or under the probability measure Q, this one tells you, so this pushing back before this existence of psi gives you in terms of probabilities. And so in infinite dimension, you don't have matrices and so on, just linear operators under some regularity assumptions are probability measures. Can be somehow represented as expectations under a probability measure. Okay, so this means that the discounted value process is a martingale. Okay. So if we reformulated now this, let's see, result from linear algebra into, which is not so easy to extend, let's say, to infinite dimension, to stochastic process. You have many states, you have general omega, you have a state space, you have many time points, continuous time, and so on. But so mathematically, in the one period finite state model, that's, as I said, a simple consequence of the separating hyperplane theorem. But we reformulated with the objective. This theorem 3.1.3 can be extended to the standard setting of stochastic processes, where you have a random time evolution of the underlying assets and so on. No? So here we state a market is arbitrage-free if and only if there is an equivalent martingale measure. And martingale measure means that the discounted financial instruments are martingales. This means SKT, asset number K at time T, divided by the interest rate. This means discounted, is a martingale under Q. In this case, we have only 2 points in time. So later we will extend this to T equals 0. Arbitrary many. And of course, at the end, the most realistic one is that you have just continuous time. Or let's say a finite time T. No, of course. Okay. This means if we have the payoff of the general financial instruments, which is also just a financial product, then we also should price this one. This should be a reasonable price. Because also S0, which is just the underlying, and this tells us under a non-arbitrage condition, this is a reasonable, as I said, a reasonable arbitrage price of. So now we have some problems. From a mathematical point of view, there might be several martingale measures. In our picture, we have actually only one, because it's R2, which we have seen in R2. Okay, you have some weird condition where this is not the case, but basically, okay, I mean, R2 we never looked at, because our picture is actually capital N equals 1. That's basically a nonsense picture. But though there might be several lambdas. Then you get several Qs, and then you might have several prices. And so a really good market is where you only have one martingale measure. So we come later to this. Yes, please.
Sir, is there any relationship between capital N and D? Because earlier
Yes,
we have
later,
taken 1 plus
yes. Yes, so it's a kind of this S, psi equals S0. Of course, this has a relation. This is in N, and this is in D.
Okay.
So in this case, it just means that you have a kind of a rank property here. We will later see that if the next step is now a second, because we had looked at the other point of view, namely replication. What we have done here, just from arbitrage, from this property to, so if we have replication, then it's even differently. What we get for each delta, for each delta t, which is just a vector in Rn, we get a phi, such that we can replicate. This is not a J, this is a delta. If we can replicate by the portfolio, this should be also just an index, but let's call it delta. It depends on the payout. This means if we can replicate a payout, this means an arbitrary cash flow at time maturity. Cash flow is just in this case a vector of length capital N. Then if we can replicate, we know that we can get a vector phi of length d plus 1, investing in our d plus 1 assets, and the value at time t of my portfolio, which is this one, equals the cash flow. In our binomial stuff, for the replication, we need this argument that we find this p star. Then we can get the price by just doing the same what we have done for S0 of the asset, of the cash flow of the assets, namely by taking expectation with respect to this risk neutral measure and discounting. So this means for every replicable cash flow at time, every replicable derivative in the sense of financial markets, if we can replicate it, then we have the unique price. So if we have arbitrage freeness, absence of arbitrage, we get the Q. If we can replicate it, then we get an arbitrage-free price, a consistent arbitrage-free price. And this one is then the only arbitrage-free price. Of course, here you ask the same question, there might be several phis. But arbitrage freeness, it must have the same value. Even if you have different phis, replicating delta, different portfolios, replicating your contingent claim, by arbitrage freeness, the price must be the same. Sometimes arbitrage freeness is also called the law of one price. That's even more, let's say, economically. So therefore, we prefer markets where you can replicate everything. And this market we call complete. A market is complete if each financial instruments, determined in this case by its P of vector delta in Rn, so means financial instrument equals vector in R. It's mathematically just another word for a vector in Rn. We call it in our world of mathematical finance, we call this derivative, contingent claim, whatever you like, your preferred term for this. Mathematically, it's every vector in Rn. And of course, by the replication argument, we have seen it just equivalent to saying You take S transpose applied to phi. So this means, in this sense, phi is invertible. And here you see the condition on N. Of course, then we need to have that you have at least as many assets as you have states. This means for all, if you say number of uncertainties, if you want to make an interpretation, number of uncertainties means the N states should be smaller than number of assets. And basically you can say it's a number of hedge instruments. You see, the replication in this sense means something that you can hedge fully the uncertainty. No? Or put it like this, you don't get additional uncertainty. No? All the uncertainty is in the underlying asset. No, this was the answer to this question, that you have a relation, that you need as many hedge instruments as you have uncertainties. And this we will later see. So S becomes a volatility matrix, more or less, and you see you need at least as a number of assets as you have uncertainties, volatilities. But so these basic structural properties are already in this one-dimensional example, one-period finite time example, where you can really see the mathematics behind. And if you learned some advanced functional analysis or something like this, you can imagine where you generalize all of this to general markets. Okay, so this was kind of recap of what we have done yesterday. Other questions? So, I mean, we have somehow done on a simple model, as I said, linear algebra, but just to introduce the basic concepts, namely arbitrage-free markets.
Sorry, sir, for interrupting you.
Excuse me? Yes, please.
Sir, I have a question.
Yes, please.
Sir, can we take delta as an infinite dimensional vector?
Yes, this you can still take. Yeah. So this means infinitely many states are the same. Of course, then you have infinite matrices. So, but I mean, yeah. In a sense, you can take any linear space if you like, to whatever you think your values are taking.
If we take delta as an infinite dimensional vector, then what will be the changes?
If you take, but infinitely dimensional vector delta means that you have infinitely many possible states. You know, it just tells you omega equals omega 1. And then you need, of course, also infinitely many instruments.
Okay.
Dimension of phi. So d plus 1 should then also be infinite in this case.
Okay.
Yeah. So all the reasoning is the same. Yeah. You have just n equals infinite implies that you need infinitely many assets in general. So it depends. So do you equip this one? It's to some extent you need, of course, a topology on R infinity. You take sequences, so L2, then you take L2 space. That's what I mean. So in finite dimension, it's just linear algebra. If you have infinite dimension, it's not linear algebra anymore. It's what's called, I would say, functional analysis, linear operators. Then you have to define what is the topology, L2 space. Usually you take L2 space. But that's not really done, because, I mean, we go directly to ST omega. So the value can be any real number, which means it's your n, capital N, becomes uncountable. But of course, then we work with other techniques. But the basic same, let's say, linear functional analysis instead of linear algebra, if you want to view it from this point of view. Okay. So, but what we next do is we extend this to many time steps, because in a market you can trade today, you can trade tomorrow, you can trade every second. So the next intermediate step will be to look at T. We now look at, here we had T equals 0 or capital T, only 2 time points. Next step is to take many trading periods. And that's already more realistic. And so this we have seen in the introducing example, this binomial tree. We had a picture of 3 time points where we can trade. And now in the picture here, that's my binomial tree. So in the binomial tree, of course, you have n time steps. What the time steps were also called n, but you have, again, only n states, because it was going up and down each time the same. At the end, here you have 2 states. Here you have one n time points. This is time point 0, 1, 2, 3, and you have 4 states. 4 potential states you have here. The n equals 4. But that's of course not the general theory. In this case, because you have a very special matrix S, if you look at it, you still find that this one, which we will later prove, that's a multi-step model. This model, under conditions we had already on P, on U and D and R, which does not appear here because it's only the risky asset, then you can prove that it's also arbitrage-free. But you prove it directly, not by going through this transition matrix and so on, because it's a multi-step model. Of course, this model is, of course, you have only n. This one we had already proven everything. You have 2 states, and you have 2 assets. So everything is fine. Okay. Okay, but as I said, we are now our next step, and that's the lecture. Basic lecture from today will extend this to okay, we have done it here already in this example. We have done it to multi-step binomial model, multi-step Bernoulli models, which gives you a binomial model. Here you see some examples, but we will now go to to page 3. No, no, so okay. So this will be our next step, is to extend this. No? Okay, now let me summarize, say it again. So how do we price a contingent claim? We take the basically what we can do, even if it's just arbitrage free, we have to check whether the market is arbitrage free. And all markets we are considering are arbitrage free. There's a very recent development which makes the evaluation much more complex than what I present you here, where we have arbitrage opportunities. In non-arbitrage free markets, it's becoming, then you don't have a unique price, by the way, so it's kind of difficult. Even if you have a non-complete market, you also don't have, in some cases, in an arbitrage free market, for products which cannot be hedged, you have a price interval. But first we have to learn, so how do we do it in an arbitrage-free market? And we will extend it to multi-period financial market models. For this, we need the theory of stochastic processes in discrete time. Who of you have learned about stochastic processes in discrete time? Please raise your hand or whatever. I don't know how you do it in all the two letters buttons. Please tell me whether this is somehow new for you. Do you use a probability space? I was talking about this before. Now, I mean, we still, if you like the binomial tree, there is still everything is at least countable for a fixed n. Of course, it's even finite. You can all put it into finite probability space, but I mean, that's not realistic, because you don't know how the price will be. You can still say, okay, we just take. Okay, there was one answer, so let me check. Shit. Okay. So I will go through this. Okay, so probability space, that means, so you have omega state of events, F state of elementary events, how this is called, F states of a set of events which are subsets of omega, and P, which assigns probability to elements of F, means to events. And F tells you, okay, that's what I want to assign probability to. That's my information I have. And so my future, what might happen in future, put it like this, and I want to assign probability to this. And as I said, if omega is everything is discrete, the most important elements of F are the singletons, which exist of one omega. But in usual cases, each, as I always told my students, so what happened yesterday actually had probability 0. Each single event had a probability 0 yesterday, or 1 second before. Because there are so many possibilities, each realization, each phenomena we see, or which will be realized, actually had a probability of 0 yesterday. Okay. But of course, such that like intervals or sets like tomorrow it will rain, this will have a positive probability. But now exactly how much it will rain, because this can be an arbitrary number how much it will rain. This has probability 0. It rains, I don't know, 23 liters per square meter, of exactly 23. Because it rains 23 plus minus epsilon, this has a positive probability. Okay, just to make the difference, it's important that your probability is on events and not on singletons. Okay, but as time goes by, in future, you might have more information. And you can be more exact about this. So these are sub, but of course, that's in this case, the setting is like this. F gives you all the information which are present in future. And so you have a sub sigma algebra, which tells you what will happen until time n. And this is called a filtration. So if in later time you know more. That's why it's called filtration. And now we imagine a time.
Hello, sir.
How it works. Time.
Sir, I have a query.
Yes, please.
How we are defining such filtration by using such a sigma algebra? How?
Yes. Yeah. Yeah. So, yeah. So, we can go back to the tree if you like on this example. So later you will see that just the information you assume that you know the next 3 days you know how the price development was.
Yeah.
This means in our tree, now the tree disappeared. My tree is on page. No, I can't move. Okay. Okay, in the binomial tree, if I'm now at time 1, let's say F1. Why doesn't it work?
Yes, sir, it's work.
F1, yeah, we are here. We have more today we are here, but now we assume we are at F1. That's now, of course, random. Assume I'm going high. In the first step, I went up. So I know now, okay, all my future events will have at least one up. So I have more information. If I assume now it's somehow, if like that conditioning, now in future I will be in one of these states. Either I'm here or I'm here.
Yes.
But if I know, if my information is where I am, I know more about my value at final time. Because here at least I know, okay, it was one up. So it will never happen if I'm here. It will never happen that I went 3 times down. Okay, you must imagine, okay, if I go one step further and I assume, in this case, there are only 2 states. I'm tomorrow, asset went up. So in 3 days, there will be never 3 ups, 3 downs, sorry.
Yes, sir.
Yeah. So that's the information so you just go by time, you have more, And just assumption, of course, you just say, okay, under the assumption. Huh? And of course,
Yes,
the contract is written here. Here you have full information. There's nothing random here. No randomness.
Yes,
Huh? So in future, of course, you
that
know.
means
Huh?
we are predicting by using these binomial trees
No, we are,
infinitely many times.
yeah. Put it like this. If we are assuming something for the future, we can predict better for the further future. Here we assume.
Yes, sir.
And then we can predict better, if you like. We know more about the future in 3 days if we would know something about tomorrow.
Yes, sir.
Yeah. Yeah. What was this 40? Okay. Yeah. So we have now these sigma algebras. And so in a finite probability space, and we have a partition, I mean, as we have done it on the tree as an example of a finite probability space, even in multiple time periods. Of course, the sigma algebra is just also a finite set of subsets. No? And so you can cut it into, let's say, you can cut first at F1, you cut in up and down. Yeah, in time 2, you cut in up, down, yeah? Down, up, down, down. Yeah? You have 4 events, potential events, and so on, and you have a finite partition. This means as time goes by, you get more and more events which you know. Yeah? Yeah, so the filtration corresponds to a sequence of partitions which become finer through time. Yeah? This means you have smaller and smaller sets. So this means if you, as the question the colleague who asked, yeah, you have more and more information about the final future if you are just going more ahead. Yeah? This means you can assign probability to smaller and smaller events. Put it like this. Yeah? Okay. Okay, but basically we don't assume it here. We just say, okay, we have a filtration which is increasing, so you have more and more information if time goes by. So Fn is subset of Fn plus 1. It's a set of subsets. We have more subsets at time n plus 1 than you have at time n. Now, and now some definitions is adapted if at time the process is adapted. Xn is our random variables, first indexed with n, but the probability Xn falls into a certain interval of values. This probability you can calculate at time n. Adapted means we know the value of time n, or more precisely, the event Xn is in a set A, in some set A. This one is in Fn. This means the probability Xn in A you can calculate at time n. I mean, it's tautological, but it just says that they have the same time. But basically, the connection between Xn and Fn is that they appear at the same time n. And of course, if we start, we do it differently. We start just with a sequence of xn's. And if we define then Fn as sigma between what the process has done until time n, like as I did it in the picture, our Fn was just, we know let's say at time, and in 3 days, we know what happens, whether it's going first day up, first day down. We know everything about the process up to time n. Then it's called the natural filtration. This might be a little bit picky at this point of view, but as I told you before, of course, this filtration, x to xn, that's just the price. The market just observes the price. But the insider, or the CEO, whoever, and that's why they are not allowed to trade, they just know more than the price. So they have more information. So an insider filtration is larger than the one produced by the price. So this totally natural, you think, for fair pricing, for market pricing, of course that's the case. But as I told you, because it was mentioned, that you can also use this for regulatory purposes. And one mathematical reformulation of insider trading is that the trader who knows or is inside has a larger filtration than the one just produced by the price. But of course, this we don't do here. We do the fair pricing model, a fair arbitrage-free, risk-neutral, however you want to call it, pricing model with all these assumptions. But basically, in the market, and if economists would tell you the market knows anything, everywhere, anything, which is of course not true, but that's all the economists also have these assumptions, and they would underscribe for this assumption as well. Okay. And so now we come further to stochastic process theory. Often you have an underlying noise like the Brownian motion. Just the like Brownian motion. And the actual observed asset price is a function of the Brownian motion. So this means you might see the entire Brownian motion, but if, for example, if the volatility matrix is not a full rank, you have less information. So there's also some, that it's general Markov process theory which connects different. So that's the definition of in probability. That's called a stochastic base. So you have omega Fp and the filtration F. That's the stochastic basis. And the financial market will be a stochastic basis with the stochastic processes on it, like Xn. Yeah, the price process. Okay, we are now coming to this martingales I was mentioning before, and now we define it. So martingales, that's a model for gambling, for fair gambling, sorry, and which is like fair financial markets. No, let's say gambling theory, the first book on martingale theory, or one of the early book on martingale theory. It's a nice title, How to Gamble If You Must. So many of these martingale theories developed out of gambling theory. Okay, so we have a stochastic basis. We call it basis here. This is omega probability space, F sigma algebra, P, and F consist of these filtrations, Fn and in N, where these are also sigma algebras, which are sub-sigma algebras of F. So F you can think about in our of the final one, but here you see it just adapted. This means X is F adapted. This means Xn in A. This is in Fn, is a set in Fn. So X is, of course, Xn all takes values in R, so that we can integrate. Like numbers, or in the financial word, money, prices. And we assume that they are integrable, and in order to take the conditional expectation. This means if I know in future the value, this is a known in future, Fn, because Xn minus 1 is Fn minus 1 adapted. So this is more or less in future, at future time point n-1, this is deterministic. I know if I know fn-1, I actually know the value xn-1 on each omega. So here's an omega, if you like. Omega. And then you see p almost all omega. Now, as I've done it before, if I go one step further ahead in the binomial tree, I actually know, because the only events which might happen up and down, but if I'm in one stage at next day, I'm either up and down, so I have only two omegas, if you like. No? No? Omega is this. One omega and the other is head, tails, head. That's one omega. So at time 1, that's actually tails, if you like. Okay. And so at this time, it should be a martingale. This means the average of the future values. So if we are actually in this state, going up and down, or let's say it's kind, we take s plus 1, s minus 1. This is only a martingale. Okay, that's a probability. This one is only a martingale if p equals 1/2. So this means if up and down is the same, we already know in our binomial tree, our p star will be 1/2. If there's no discounting. Okay, so all this discounting and the geometric growth and so on is kind of hides the basic martingale property. That's why we say the asset value discounted will be a martingale. If you have no discounting, the asset value itself is a martingale. If we assume it's you go the same percentage up as you go the percentage down, then this will be a martingale. But we will see this example later, the proper binomial tree, which gives you a martingale. Okay, this is important. My future average value. Okay, my prediction for the future, put it like this: if you predict by expectations, and many estimators adjust the expectation of the random variable, like if you predict the parameter mu in a normal distribution with parameters mu and sigma square, your prediction of your future value is the mu itself. Quite often, prediction is based on this. We would say, okay, the prediction of your future value given the value 1 day before with the value 1 day before. It's fair. Meaning in a game, if xn is your current gain in a game, if it's a fair game, like a coin toss, like here, on average you will have the same. Of course, as you know, every game is not fair, because like in lottery, of course, the lottery company will always make a gain. And even like in the casino, if you play roulette, it's not fair, even if you put on red or black, because they have the green 0. Then only the casino will win. At least in probability, if I teach stochastic processes, of course, it's always telling me every game you play is not fair. Don't do it. Or you have your own casino. And here are some examples of this. So that's if your increase is independent from where you are, and on average you have 0 increase, like in the binomial tree, your increase with a Bernoulli variable going +1 or -1 up and down the same amount, then it's only fair, if the mean is 0, and in a mean 0, it's only in the case where p equals 1/2. So this means independent. IID means identically independent distributed random variables. Or that's the one we more or less have here, because we have multiplication. Financial assets. Or assets like equities, because they grow. You say, okay, I have an increase by 10%. This means current value times 1.1, or current value times 0.9, and so on. You have multiplicative because it's growing. That's like inflation, whatever you want to. Like you feel always richer, but the money is always less. In numbers, you're getting richer, but in real wealth, you probably don't get richer. Okay. So this means, this is a martingale if on average, you multiply by 1. It's clear. That's the type of martingales, of course, we will consider, if you like. Because. So how familiar are you with conditional expectation? Do you learn it in probability as a standard class, standard topic?
Yes, sir.
Yes, okay. So that's important here because it's connected to the information and going forward and so on. Okay, so that's a martingale. In our case, if Xn is your wealth or your profit in gambling or the share price of an equity in your portfolio, then this one, the increase is a delta. This should be giving rise to a martingale. And then the increase should be, you can also put it like this, the increase should be 0. Now we come to a very important concept connected to mathematical finance, but which is also very valuable for stochastic analysis in general, or theory of stochastic processes. That's what's called the martingale transform. Or sometimes are also called stochastic integral in discrete time. So imagine you have your trading strategy is now your investment strategy or your gambling strategy. How much you buy from stock Xn at time Fn minus 1. Now you see, it's a specific process where you know the value already, let's say n equals 1. Now we are in the period today 0. Now I decide how much I will invest in stock Xn. Or what's my stake of gambling on the game Xn, if you like. And if it's positive, I get it. It's negative, it will be negative. So imagine you have decided on time n minus 1 to invest the amount Cn in a stock which costs you Xn minus 1. Then your gain until next time, let's say tomorrow, today is 0, and your gain tomorrow the value of the portfolio will be Cn times Xn. So your gain, yeah, that's also, if you like, gain from investing. Cn in xn. Yeah, but at time n minus 1. Also, what we have, we have done always on our single binomial model. We had say, okay, now I have to know how much I have theta 0, theta 1 was this called, how much do I invest? Yeah, and then your gain, yeah, is this bit, is your gain over each time period. Yeah? So this means your gain of your entire strategy, always investing at time k, investing ck, is this yn. You just add up your profit and losses from your trading strategy. Yeah? Next time you decided C2, next time C3, and whatever you do on C, on investing in stock X, yeah, will be accumulated to what's called the martingale transform. And of course, numerically, there's nothing else as a discrete type of integral, summation. Yeah? You sum values times deltas. Yeah? The nice thing about it, and that's why I also mentioned this before, also the value process or the discounted value process, the value process of your hedging strategy discounted will also be a martingale. This comes from the fact, yeah, that your every trading strategy, the value of a trading strategy is of what's called of a self-financing trading strategy, which we will define later, is always a martingale. And that's why you discount, you have to discount it and so on. But basically, if you start with a martingale, then you get a martingale. So in gambling theory, this seems if your game is fair, yeah, and your trading strategy is like, and then any trading strategy will not give you profit. Of course, only if it's a bounded, non-negative, predictable process. So you need some assumptions. If you have unbounded resources, put it like this, then of course you can make a gain. But then you need already to have unbounded an unbounded amount of money. Then you can do it. So this is a statement. If you have a bounded trading strategy, unpredictable just means that Cn, what I invest, this event, I already know one time before. I have to decide now what to invest. I cannot wait, look what the value will be tomorrow. I would invest this amount in this asset if it goes up. You have to decide it today without knowing whether it's going up and down. And this means mathematically, trading strategies always have to be predictable. Predictable. Okay, there's a typo. Yeah, so predictable, so from a mathematical point of view, you have now processes which are adapted, like the price. And then you have processes which are predictable, meaning you have to do it one time unit before. Now you can think about, if you like mathematics, what does it mean for continuous time? The one is less continuous, probably, or whatever. Yeah, so you have some continuity of your decisions. Okay. And so we can calculate the conditional expectation, and you can, if Cn is Fn measurable, you can put it out. That's why I asked you, conditional expectation. Yeah, you can put it out, yeah, and then you get super martingale. That's the proof of super martingale. Super martingale is the general theory, but consequence of this, if C is bounded, then we don't need non-negativity. We get this. If this is a martingale, this is 0 if martingale. Then it's also 0. So this means the increase over time interval is 0. Time step is 0. So this means if you have a fair market, or if you have a fair game, as long as you have a bounded strategy to make money out of this gamble or make money out of this market, you will never make it on average, of course. You may be lucky and you are on your own path. In the future, you might be lucky. But on average, you must be lucky. You cannot be smart. You just must be lucky. I hope you teach this your students in probability as well. Okay. Okay. And so there's some. Let me see how much time I have. Okay, so martingales have very nice properties. For example, under some conditions, they converges as n tends to infinity, but that's not interesting for us currently because we are on finite time. What's more interesting for us is what's called stopping. Because some people think, okay, I have a very clever strategy. I stop when I make a gain, when I make my first gain. That's what's called the doubling strategy. But you can also do other exit strategies. To just play, just set what you have, put in again what you have earned so far, or whatever, or you have lost, but you double. And then perhaps this doubling strategy, if you have like in roulette, where you are, it's almost fair. You ignore the 0, put it like this. So black and red with probability 1/2 is your assumption, and then you double. And first time you get, let's say you put on red, first time you have red. If you double, and first time you have red, you will make a gain of €1. But you can also do other strategies. And mathematically, these strategies, this exit strategy, are called stopping. But you also know if you have it's called stopping times. That's like this could be a typical strategy, also like say as a trader. You just keep your portfolio and stop at a certain time. That's what's called, and then you exit, you sell at the optimal time. Okay, we already have the you already have the result. This also doesn't help. If you have a stopping time, and stopping time, what's the property of stopping time? At time n, you have to know whether you have stopped or not. This means the event that this tau is small happens before time n has to be in the sigma algebra F index n. No, that's almost clear. You can't say, okay, I wait until tomorrow and then I say, okay, yesterday I would have stopped. No? Of course, there are times that, what is the stopping time? Yeah, it's a natural number. Minus, of course, it's plus. Plus infinity. If the event, no, whether you stop at time n is in the filtration Fn. Bounded stopping time is if the probability that you have some large number k, but the probability that it stops before this large number k is 1. And it's a bounded one. Now, typical stopping times associated to a natural filtration of a stochastic process is what's called the first exit time. In order to be safe, I say, okay, I'm not really do not want to make most of the money I might get. I just say, okay, if I earn 100 euros, I stop. If my wealth xn is larger than 100, I exit. This means in this case, my B would be the interval from 100 to plus infinity. But so, as long as this don't happen, I play. Okay, that's adapted, as you can see easily. So this is a stopping time. But then Dupe, who more or less invented the theory of a mathematical theory of martingales, because a lot of this goes back to Dupe. And he already figured out, okay, but then on average, you also don't gain. As long as you have a bounded stopping time. So this means the stopping time I was telling you before, you wait until your first first time red in a roulette is not bounded. It can take any value. There's no k. It's the same as we had before, that your stakes must be. You only have in the mathematical sense of view, you only have arbitrage. If you have either infinite long time to wait, which again implies that you have no problems to lose billions of money in order to earn €1. Because you lose all the time, and it might be after 1,000 games that you make your first gain. And of course, to the number 10,000, 1,000 is very high. This money you need, or somebody has to lend you or whatever. Okay, this also does not help. So fair remains fair. So I just mention it shortly because pricing American option, that's of course also related to what's called optimal stopping. So this American option, which on the binomial tree, I don't know whether you have done it or whether we will have it on the binomial tree, can be priced easily. So the theory behind it is this optimal stopping. I just mention it in the last 5 minutes I have today. I will say something on optimal stopping.
It's okay, sir. You may continue in the next lecture also. That's not a problem.
Yeah, okay. the optimal stopping. How is this related to option pricing? That's what's called an American option. Yeah, an American option gives the holder the right to execute the option at any time before expiry. Yeah? This means an American, you see an American put option. I do put options because call option we have seen by arbitrage argument, there's the same price as the European call option. So if you execute at time Tor, then you will get K minus XT 0. This means if XT is XT is smaller, then it's going, the payout was like this. That's your payout of your call option. Here you have K, and that's your, if XT is 0, your maximum profit is K. And you see now at a certain time it's here, now I execute. Xtor is this value, so this will be your profit.
So one general question,
Yeah.
do this control people work in this direction? I mean, how to find this? I mean, control is involved, control theory is involved in this problem?
Yes, you could, I mean, yes, so put it like this. So if you, from a control point of view, the your portfolio investment, which we call phi most of the time, that's your control. Yeah, so your control process is phi scalar product with the assets, and you want to have conditions on this, on these stochastic processes by choosing a proper phi.
Okay.
Yeah, for example, do the replication. Your concern on the, your boundary or your conditions on phi is that like phi t times xt equals your option payout.
Yeah.
Yeah, and then under some conditions you get the same as the Black-Scholes formula.
Okay. Okay.
Yeah.
And
so yes, so I was searched. So like if you have a bid and ask spread, some people solve it by control. Yeah, they have also assumption on the bid ask spread, but the general approach on this bid and ask spread, instead of considering only one process, ST, the price process, they consider two processes: the bid, the upper, and the lower price. Yeah? You do everything what we do here with two prices. Also replication, of course, they know if you sell, you have to pay this price. If you buy, you have to pay this price. Other way, if you buy, as you buy, if you buy, you have to pay more than if you sell. Yeah? But if this is also for each market participant, then you get a pricing interval. Huh?
Yeah.
Yeah. But you do the same procedure like this, and you can also formulate it in terms of a stochastic control.
Yes.
Yeah. So it's there might be a book from Davis, but I couldn't find this book. But there's of course some literature, so I can show you. Stochastic optimal, the lecture note. Yeah, there you can check. They also consider a bid-ask spread in this context. Yeah?
Okay, sir. Okay, sir.
Yeah.
We'll note it down. Yeah.
Yeah. Okay. 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 This means, this is your payout if you execute a time Tor. Tor might now depend on the path or on the trajectory where you are. Huh?
Yeah.
So in the binomial, yeah, so it's in this sense a function of omega, huh? But it must be, you must know whether tau is more, it must be a stopping time. Yeah? You must know at time n whether you want to stop or not. Huh? So this means, yeah, if you execute at time tau, this will be your gain of this put option. Huh? So this means you are now the holder of the option. You want to maximize your profit, of course. Huh? So what you do, you take the all stopping times, which terminates before final time, and take your expectation. That's, of course, Q. Huh? Again, under the martingale measure. You know there's only one martingale. You have a nice market still. Now you have the more complex problem in a complete market to price your American option. Yeah?
Yes.
So you have to maximize over all stopping times. Yeah? And that actually was developed before mathematical finance. This type of processes were the optimal stopping problem, which were solved in a different context already. And I will probably continue tomorrow on this topic. Okay.
Yes.
Thank you very much.
So, thank you, sir. Thank you so much. So now we wind up this session here, and the next lecture will be at 2:30 Indian time. And sir, your lecture is scheduled for tomorrow. So
Tomorrow
thank you
same
once
time.
again, sir. Yeah, tomorrow same time.